On today's episode, we are getting into the latest space news, including after 15 years, scientists make a massive new discovery regarding our universe, and Europe test fires their new reusable rocket for the first time. A scientific discovery on the universal scale has been published, seeking to prove one of the last big predictions from Einstein's theory of general relativity, and the method for detecting this discovery took researchers 15 years, 3 of the biggest radio telescopes ever made, and a detection arrow that spanned light years. On June 28th, the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, posted a report to the Astrophysical Journal of Letters. In it, the organization, which is made up of over 190 scientists across 70 institutions, detailed their 15-year study, which seemingly proves the existence of gravitational waves at the cosmic level, a literal background hum of the universe. Now, gravitational waves are not exactly new. They were theorized a while ago, and scientists have been spending a lot of time trying to measure them. The basics are that anything with mass emits gravitational waves when interacting with other things that have mass. These waves are just like ripples in a pond, except instead of water, gravitational waves move and bend the fabric of space itself. If you bump into a coffee table or swat a fly, that causes a wave in the gravitational fields that we all emit. Obviously, things like flies, coffee tables, and people are too small to cause ripples that are noticeable. In fact, even something the size of Earth or Jupiter or even our own sun doesn't have enough mass or acceleration to produce gravitational waves that we can detect. For that, we need black holes, and more importantly, they need to be eating each other. Black holes are usually formed by stars much bigger than our sun, so even small ones tend to be large enough to notice when they act oddly, and as it turns out, black holes do manage to do some weird stuff. The most useful scenario for catching gravitational waves, though, is when one black hole swallows another. Sometimes these swirling masses orbit each other just like binary stars, and this often ends in the pair slamming into each other at extremely high speeds. This is what LIGO discovered. The Laser Interferometer Gravitational Wave Observatory was fully constructed in 2014. It's a multi-kilometer-long detection array which uses finely tuned lasers to sense gravitational waves on the sort of scales that we've been talking about, and in 2016, they recorded their first real proof of gravitational waves. 1.3 billion years ago, 2 black holes, each about 30 times the mass of our sun, collided out in the universe. They produced such an incredible amount of energy that LIGO was finally able to make a definitive detection of the waves in space that were produced and confirmed Einstein's theories. Now, we had to go over that because you needed to have some understanding of how hard it is to find these waves and the scale of energy needed to make them, because Einstein predicted something way bigger. The idea was that if large enough masses could produce gravitational waves that we could detect, then there should be objects so massive floating out in space that the ripples they make would form a sort of background hum, a frequency whose wavelength is so colossal that they span light years. The gravitational wave background. Think of it as sort of the ambient swell of the ocean. Everything would be affected by it, but being inside those enormously long waves means that you wouldn't really notice unless you had a detector sensitive enough. And now we're getting to the really wild stuff. Waves at that scale means 2 things. First, they would have to be created by binary supermassive black holes slamming into each other. Every large galaxy has one of these supermassive black holes at the center, millions of times the mass of our sun, or even regular-sized black holes. We've observed even the one that sits at the heart of our own galaxy, so we do know they exist. What we're not sure about is if any exist that orbit each other in a binary supermassive system. Einstein theorized that some of them would have to exist, and that they would be moving so fast that they would have to be emitting this background wave, especially once they collided. And that brings us to the second thing. We were going to need an astronomically sized detector array if we hoped to find this wave. Remember LIGO? Kilometers of array space using a delicately tuned laser beam to detect just a normal black hole eating another one. There's no hope of using something that small to detect a gravitational wave at the scales we are discussing here. So the scientists at NanoGrav built themselves an array that spanned across the galaxy, and to accomplish that, they used pulsars. Pulsars are stars that were not quite big enough to become black holes. Instead, they collapse into super dense cores, spinning incredibly quickly, regularly sending beams of high-intensity radiation out into space. Every once in a while, we detect these beams like cosmic lighthouses. Pulsars spin incredibly regularly, and sometimes they also eat a binary sibling, which leads them to spinning even faster. Astronomers call these millisecond pulsars because they complete a full rotation in under a single second. And it's these types of pulsars the researchers used. Think of it like the laser beam at the LIGO array. Gravitational waves bend the fabric of space, literally bringing 2 points closer and then further away from where they started. At LIGO, scientists measured the laser beam for the amount of time it took to reach their instruments at the other end, kilometers away. They know the speed of light, so if there was any deviation, no matter how small, that was confirmation. So when the nanograv researchers audited the millisecond pulsars they found, they studied the spin rate of each individual one. Then they waited and took careful notes across 68 known pulsars over 15 years. This pulsar timing array is an ingenious way to use the universe as a tool, and it worked. Over the course of the first 12 years of the study, the team used the now decommissioned Arecibo telescope, the Very Large Array, and the Green Bank telescope to measure the changes in these pulsars. And over the next 3 years, they gathered and analyzed the data, finding that these pulsars were being pushed and pulled on waves that spanned light years. The biggest takeaway from a study like this is that now we know that supermassive black hole binary events likely exist, or an equally large event. Either way, it helps solidify Einstein's theory of general relativity, a fundamental part of our understanding of the cosmos. More practically, though, this study shows a new method for detecting phenomena at an amazingly humongous scale. Gathering easily verifiable data from stellar objects light years away is an application we could use to figure out other big questions we have about our universe. On June 22nd, the Ariane group successfully test-fired Prometheus, the engine that will be powering the European Space Agency's new fleet of reusable rockets. The prototype 3D-printed engines were brought to the Ariane group's test site in Vernon, France, and mounted on a Themis first-stage booster and lit for 12 seconds. Prometheus can put out 100 tons of force and normally runs off oxygen and methane, just like a lot of other engines in the industry. But for this burn, Ariane Group decided to test the use of both normal and biomethane fuels, showing that the ESA's Prometheus-equipped rockets will be versatile and environmentally friendly. These two pieces of hardware were commissioned in late 2020 and are part of the Ariane Next joint, a joint venture between the European Space Agency and the French CNES, with Ariane Group as the primary contractor. The ESA has been using Ariane Group for some time now. This company has designed and run most launch hardware for the ESA since it was formed in 2015. Vega, the European version of the Soyuz capsule, and of course Ariane 5 and 6, the last of which is still in development. So it's not surprising that Ariane Group is running the show again for this next chapter of European spaceflight. What is surprising is how they're going about it. You all might notice that both the Themis module and the Prometheus engine looked a little rough in this test. Prometheus didn't have its nozzle extensions, some combustion tech wasn't quite ready to be tested yet, and Themis itself wasn't exactly a complete booster yet. This is because the Ariane Next project is designed to run on a tight budget, with tests happening as early as possible in the development cycle in order to help the engineers learn and iterate as quickly as possible. And if this is all sounding a lot like how SpaceX does things, then you are extremely correct. Up until now, Ariane Group had been known for playing things safe. They have been criticized for requesting more budget than would be necessary, but with the ESA falling behind in launch utility, it seems Ariane Group has decided to see if they can use a SpaceX-style approach in order to develop a competitive vehicle system that will have versatility and, more importantly, be extremely cheap to operate. And the real key to that is the fuel type. Up until now, Ariane Group's designs have made use of hydrogen as the main fuel, similar to NASA's SLS rocket. Hydrogen is very safe for the environment, not to mention extremely efficient, but it needs to be stored at very low temperatures compared to something like methane. So not only can the new engines use a fuel type that doesn't need to be so cold that it changes the shape of all their plumbing, the methane fuel can be stored in a denser package, allowing Themis to use smaller tanks and take up less space. Testing for the new Prometheus engine will reportedly be ongoing for the rest of this year, with the goal to reach a SpaceX-style hop test once the landing legs for Themis are figured out. It will be very interesting to see if the ESA can copy the success of companies like SpaceX. Area Next is in very early days still, but a live fireburn conducted this soon into its development would seem to be pointing to them being on the right track. Meet us back here every week for more updates on everything aerospace industry and interstellar exploration related. Make sure to give the video a thumbs up today if you liked it. That really helps us out for real. And subscribe to the Space Race for more videos just like this. We do one long-form essay and one news update every week. And if you'd like more, we've got 2 more on the screen for you right now.